I'll be opening a new topic, and this is about fuzzy logic. We're done with the case-based reasoning, but this time we will go with the fuzzy logic. Let me just have a print screen of this to know your attendance. Let me just have a print screen of this so that I could report to the college who are attending the class and not attending. I hope you can see my screen clearly, and please inform me if something goes wrong so that I could do the proper adjustment on my side. So once again, good morning, ladies and gentlemen. Today we'll be opening a new chapter, which is fuzzy logic, and I guess we were done with the case-based reasoning, and I gave you plenty of examples last time. I guess you already had a full grasp of what case-based reasoning is all about. So this time we will be using another technique in artificial intelligence to use in solving problems. So this time I'll be introducing to you fuzzy logic. Okay, to prepare you regarding the concept of fuzzy logic, let me ask you two questions. The same thing I have done in the case-based reasoning. To prepare you for the concept, let me ask you questions in preparation. So I'm showing you pictures here. I have three pictures here, right? Maybe all of you are familiar with this. So on the first picture on the top, on the left top of the screen, you are seeing two animals, right? Can you tell me the two animals? Can anybody
Crocodile.
from on the left, this one, the one I'm pointing out? Let me just use a pen.
Tiger.
Tiger and
Lion.
tiger and the lion, right?
Lion.
So can I ask you, Riham, which of the two is the tiger and which one is the lion?
In the right is lion.
This one? This one is lion?
Yeah.
Are you sure?
No. That's second.
Yeah, very good. So this one is the lion. Okay. And this one is the tiger. Very good. So Riham is confused, right? This is really confusing. Actually, the truth is some people, they don't know the difference between a lion and a tiger. That's very true. Actually, you'll be confused if you don't know the features of the lion and the tiger, right? Okay, Tarek. So there are names here. Basically, we know which is crocodile and which is alligator, right? So my question is,
yes,
how we will know that this animal is crocodile and this is alligator? How do we know?
and the mouth.
Very good, the mouth. Because normally, a crocodile has this kind of mouth, right? Correct? This is a crocodile.
Exactly.
And an alligator is having this kind of mouth, right? Very good. So how about Ibrahim?
Yes,
So
doctor.
it says in here turtle and tortoise, right? How did you know this is turtle and this is tortoise?
Yes.
How we will know?
This turtle will be in the sea.
Okay, very good. It's living in the sea.
Turtle is not going in the sea.
And tortoise can be in the land, right? Very good.
Land, yes.
What if we remove both? Let's say we will remove turtle and tortoise. Let's put them both in the land. How will you know it's tortoise and turtle?
This shape, this hands of turtle are long
Very good.
for swimming.
Yeah. So the hands were designed for swimming, right? Good.
Yes.
Very good. So you're able to distinguish them because we were informed on the major differences between a lion and a tiger, a crocodile and an alligator, and also a turtle and tortoise. That's very good. But if you were not given this information, this is difficult to distinguish, right? Because both these animals they share common traits, correct? If I represent it in Venn diagram, this is the tiger, this is the lion, and they share something in between, correct? And actually this
Yes, they are empty.
very good. So normally these things that they share in the middle, we are confused, right? So this produce some confusion. So people are quite confused on these shared properties. Let's say, for example, both of them they have this, right? Both of them they have this hair here in the mouth. Mostly the features they have similar. So there are only some differences. These are the differences, okay? Those which are not shaded, we call them the differences. So there's some differences in these two animals that would differentiate a lion from a tiger. But if we will not know the differences, we might be confused. Correct? So there are some situations like this when two elements or when two objects they share common properties which might lead us to confusion. Okay? It might lead us to confusion. And let me ask you another question. Aha, good. What do you see in my screen? What do you see in my screen?
People.
Good. What more? Abir, what do you see in my screen?
Also white. It's white of people.
Mm-hmm.
We see this length, this tall of people.
Yeah, very good. The height of the people. That's very good.
Height.
Very good. We're talking about the height, right? So this is Ibrahim, maybe. Maybe this is Ibrahim. And this is me. This is Dr. Ferdy, maybe. Right? because I'm
Why,
very
doctor? You tall, doctor.
ano, I'm very small, so I'll be here in the 5'1". So maybe Ibrahim is 6'4". Or Mr. Tarek would be this one in the middle, right? Okay, going back with this example. So I gave you some illustration here. I've said earlier Ibrahim is 6'4". So we could say that Ibrahim is tall, right? No problem for this. Because based on this collection of data that we have, this person here, we can say this person is small. Dr. Ferdy is small because obviously he's the smallest in the group, right? And Ibrahim is the tallest. We know it. Okay? We know it. No problem for that. Basically, we know because Dr. Ferdy is the last in the list, and Ibrahim is also last in the list, which is the tall one, and I am the small one. Now, how about the people in the middle? That's my question. How about the people in the middle? Let's say for this person, can we categorize this person as tall?
Medium, doctor.
No, I'm only asking between two values. If I ask you about small and tall, what can you say about this person? Is he tall or
Tall.
is he small?
Is tall.
Because if you will
Small.
say, it is tall, Ibrahim is tall, right? So you cannot say this guy is tall,
Tarek,
right?
Tarek say small.
If I say it's small, it's not fair that we have to call this guy small, right? Because this is obviously very small. So there is now a confusion, correct? Now, if we follow Ibrahim's discussion earlier, he said, "Doctor, this is medium." That's correct. If we put a third parameter in our discussion, and let's call it, let's say, medium. So this guy is in the medium, right? Medium height. So no problem for that. If we divide the group into two parts, so this guy will be in the medium, correct? Now, again, if this guy is medium, as Ibrahim said earlier, how we will categorize this person? This one. Is he small or medium? It's a big question mark, right?
Doctor,
Tell me, please.
he is small, which if we take from the right side. If we take from the left, he is medium.
So difficult, right? Actually, you are very
Yes.
right on that, Ibrahim. If your point of reference is from the left, then you could say this guy is medium, right? But if your point of reference is this one, you can say he is medium, correct? So I mean he's small. That's very good if your point of reference is here. So here comes what do we call the concept of fuzziness. Okay, fuzziness means we are confused. It's not clear. We don't know really which is which, right? So because the problem with the computer system, okay, the problem with computer system is that if we computerize everything and we want to program a machine to distinguish things, the problem with our current machines is that it recognizes only two values. If you are small, it's 0, right? If you are tall, it's 1. Agree? Because our modern computers, they run in binary format. So meaning 0, 1, 0, 1 or 1, 1, 0, 0, something like this. So if you are small, it will be represented by 0. If you are tall, it will be represented by 1. But the problem now is, how about those in the middle? How could we categorize these people in the middle and represent it in the machine form? So this is now the problem, right? So how do we put the range between 0 and 1? So in digital, we only represent values into two, 0 and 1 in digital. But in analog, one good thing with analog is, if we have the x-axis here, analog can represent things in this way, right? Is analog, correct? Is for analog. For digital, we represent values in this way. Okay, this is 1, this is 0 for digital. So mostly our computers are digital. So this is now the common problem, right? Since we are running digital machines, it could only recognize two values, 1 and 0, 0 for small and 1 for tall. The problem now is the values in between is a big problem. But in the analog, if you will see, analog, anything on the top is 1 and anything in the bottom is 0. That's why you will see there is a transition, right? Have you noticed this? From this point up to this point, there is a transition, correct? So as the curve goes down, the value changes. This is 1, this is 0 here, this could be 0.1, 0.2, so on and so forth up to 0.9 here. So if you will see, as you go down with the curve here, the values is represented. Correct? So in fuzzy logic, our concern is how do we convert these analog values into digital and vice versa. Okay, so how we convert analog into digital and digital into analog and vice versa. You have to remember, in the digital form, the value should range from 1 up to from 0 to 1. Okay, this is our concern. But in the analog, it's a real life counting. Okay, it's not limited to 1 and 0 only. It could be 1, it could be 1 to 100 or 1 to 1000. So this is the power of analog. Okay, analog is representation of any value from 0 to infinity. So let's say, for example, to represent this value in analog, we could have 5-1, 5-6, 5-10, 5-11, 6-1, 6-2, 6-4. This could be represented in an analog format. So maybe Ibrahim is 6-4 here, and then this one is 6-2, this one is 6-1, so on and so forth until we get the smallest one, which is 5-1 here. So our goal in fuzzy logic is how do we convert real life value like height, weight, distance like this into computer format, which is 1 and 0, ranging from 0 to 1. Okay, so this is our concern with fuzzy logic. So we want to categorize in fuzzy logic. We want to categorize, is 5-10 really 1 or 0, or is 6-1 really 1 or 0? We want to categorize it. We want to remove the fuzziness or the confusion between two values. So basically we know this one is 1 and this one is 0. There is no debate on this. We know it. 5-1 is small, no debate on this. 6-4 is tall, no debate on this. The debate or the argument is only in the middle. We want to determine these people in the middle. We want to categorize them. Are they really small or tall? So we can solve it using this technique in artificial intelligence, which is what do we call fuzzy logic. Okay, again, fuzzy logic entails a lot of mathematics, so you have to prepare your pen and pencils as we go with the calculation, because it will take computations. But don't you worry, computations involved in fuzzy logic is not that complicated. Okay, it won't ask you to do integration or other thing. Just the basic algebra is enough for you to be able to grasp and calculate values in fuzzy logic. So you have to remember, fuzzy logic is a system. Okay, it's a system. You have inputs. Okay, we have processing in the middle, and then we have output. It is a system. You have to remember that. So it is a system. Okay, so there is processing in the middle. Okay, so you have an input and then you have an output here, in and out. That's why we call it a system. And then fuzzy logic is using these concepts of what we call membership function. Okay, you will now see, maybe you're having an idea what I'm talking about on the membership. So the membership function determines which group belongs to tall and which group belongs to small. So we have functions, right, to determine the membership of the data. Either it's categorized under tall or under small. And then we will be calculating the problem, and we need to provide a solution using this fuzzy logic system. So we will do some calculation in order for us to provide a clear solution to the problem. Ready? Let me begin. So I have an article to give you but this time we cannot read it because we are not in the classroom. I won't be able to give you this to read, but maybe after this discussion I'll give to you the article, and I want you to read it and try to answer these questions I posted in this PowerPoint, and you can tell me the answers later on. Maybe we can do it in the chat box. So I want you to answer these questions. Anyways, the PowerPoint is available in the Moodle. You can download it anytime and you could have a grasp of what I am discussing in this session. So let me introduce to you first the fuzzy logic system, or we call it the FLS. So the fuzzy logic system is a non-linear mapping. Okay, it's a non-linear mapping of an input data set to a scalar output data. So I'm talking about some technical terms here, but we could have a full grasp of them later on as we go with the discussion. So you have to remember, we are trying to map non-linear values. Okay, so when we say non-linear values, this could range. Okay, this could range from 0 up to infinity. Okay, so we call it non-linear mapping. So non-linear values would be from 0 to infinity. When you say scalar, they have scale. Let's say, for example, 0 to 5, this could be short, and then 6 to 10, this could be long. Okay, and then 11 to 15, this could be, let's say, extra long or very long. Okay, so meaning this is what we call a scalar. They have scale. Okay, we are putting some scales on it. Okay, when you say non-linear, meaning this could be a value from 0 to infinity. It could be from 0 up to 15. Okay, so we call that non-linear. So when you say scalar, we have to represent them in this form: 0 to 5 short, 6 to 10 long, 11 to 15 extra long. So this is how we represent things. So in fuzzy logic, from non-linear mapping, the one I told you, 0 to this, we will represent the data into scalar like 0 to 5, so on and so forth. So investigating on the parts of the FLS, or the fuzzy logic system, it has a falsifier. Okay, it has rules. You have to remember, we have the rules, and from the rules we are doing some inferences. You know inference, right? So inference means, inference can be said to be like a conclusion. Okay, or it could be a decision, something like that. Okay, so based on the inputs of the falsifier, we can do some inferences. Okay, so the one I told you earlier, if it is 1, it is tall. If it is 0, it is small. So this could be provided by the inferences here. But of course, the inference is based on your rules. Okay, so rules dictates what conclusion or what decision you're going to make based on the rules. I hope you got it. And then we have the falsifier. Okay, so the falsifier, let me just discuss to you the difference between the falsifier and the falsifier. If I have it in here, I don't have it in here. Okay, let me just get it. So the inputs the inputs for our fuzzy logic system, we call them the crisp inputs. Okay, we call them the crisp inputs. So these crisp inputs are normally non-linear values. Let's say, for example, we could use here, let's say, for example, 6, 5. I'm sorry, it's a wrong representation. Let me just erase it. Let's say, for example, 6, 5. Okay, So 6'5" is a height, correct? 6 feet 5 inches, or it could be 100 meters, or it could be 1 kilometer, okay, or it could be 1000 OMR, okay. So all of this, we call them crisp, okay, we call them crisp. In short, crisp inputs, we are referring to real life values, okay, we call them the real life values. So like 1000 OMR, 6 feet 5 inches, 100 meters, crisp inputs. Just remember, when I say crisp inputs, I'm referring to real values, okay, to real values. So these crisp inputs, we have to falsify them, okay, we have to falsify them. When we say we have to falsify them, we have to convert these real inputs into either 0 or 1 or in between, okay. So the output of the falsifier is the conversion of these real life values into 1 or 0. So maybe after falsifying 6'5" will be represented by, let's say, 0.99, okay, or so in short, the value of the output of the falsifier is a value between 0 and 1. You have to remember that, the value between 0 and 1. So this value of 0 and 1, we're going to feed them in the inference engine, and based on the rules, we have to decide if these crisp inputs, these fuzzy values that we've got are categorized properly into tall, small, or medium based on the rules here, okay. So after passing these values in the inference engine, and we determine the decision or the conclusion based on the rules, we can now defalsify them. So defalsifying means from 1 and 0 values, we will convert them back into their original form, which is in this, okay. So again, we will convert these values that we obtained from the defalsifier into real life values, like 1000 OMR again, or 700 OMR, 95 meters, something like that. So again, let me just repeat: real life value to 1 and 0, to binary, and here from binary to real life values, okay. So this is how our fuzzy logic system works. So there are steps that we have to follow in fuzzy logic, which we will discuss one by one later on. So first, you have to define your linguistic variables and terms, okay. Define your linguistic variables and terms. Let's say, for example, if you're talking about height, okay, if you're talking about height, and then your variables would be height would be, the terms you will use may be tall, medium, or small. That's an example of your variable, right? Or if you can talk about weight, it could be heavy, light, or medium. So you have to define your variables, meaning these are the variables and terms that you're going to use all throughout your fuzzy logic algorithm. And then after this, you will construct the membership functions. And let me remind you, friends, that in this process you are required to do some mathematical manipulation here. So some maths are required, okay? Some maths are required here for the membership functions. Then after this, after you perform the membership function, then you will be constructing the rule base, okay? So you have to create your rules. So you should have your rules Okay, so series of if-else statements here will be done for your rule base, and then from there you have to compare and determine the conclusion based on your membership function values. Then after this, you have to convert your crisp input into fuzzy values. We call this process as fuzzification. Okay, so we convert real life values into fuzzy values using the process of what do we call fuzzification. And then based on this value, okay, of the fuzzification, you will now evaluate these values if they correspond to certain rules. And then from the rules, you will now combine the results in each rule and then provide an inference or conclusion or decision. Then after this, convert the output data to non-fuzzy values, and we call this process as excuse me, we call this the fuzzification. So we have 7 steps to follow for fuzzy logic, and we will be doing that one by one in this example. Okay, so let's try to go with this one. This is one of the most important part of fuzzy logic, the membership functions, and I want you to understand this fully, because if we will not get the full concept of membership functions in fuzzy logic, we won't be able to do fuzzification and defuzzification. Okay, this is a prerequisite, fuzzification and defuzzification. So we have to understand these membership functions. Okay, so a membership function is used to quantify a linguistic term. We have to quantify it. Normally, the output of the membership function is the values between 1 and, between 0 and 1. Okay, so this is the result of these membership functions calculation. So after performing calculation using membership function, which is actually the process of fuzzification, you have to remember fuzzification requires membership function, okay, to operate. So after fuzzification, after subjecting your real life value or the crisp value into fuzzification, the output of fuzzification will be values between 0 and 1. You have to make note of that. So in fuzzy logic, we are using plenty of examples of membership functions. We have the triangular, we have the trapezoidal, we have the piecewise linear, we have the Gaussian and singleton. So in this session, we won't be discussing the last 3 mentioned ones, the piecewise linear, the Gaussian, and the singleton. We won't be discussing them in this example, because these one are used for highly advanced processing, like when you go with image processing or signal processing. Normally Gaussian is being used, but for the sake of this discussion, normally we will be using triangular and trapezoidal. This would be enough to solve common real life problems. So let me introduce to you this membership function. Look at this. If you will see this representation here, this is trapezoid, right? Okay, so this is very simple. So if you will see all the points here, they are represented by letters. Okay, these endpoints here are represented by letters for the trapezoid. This one here is A, this one here is B, this one here is C. So they're represented by letters. Same with the triangular. Each vertex is represented by letters as well. So this is B. Okay, so in the Gaussian, it's represented by a curve, okay, a parabola, and then we have this we have S from this side up to this side, and from here up to here we call it M. And for singleton, we have A and we have B. But this won't be covered in this discussion, but we will only focus on trapezoids and the triangular. So these are for highly advanced processing in fuzzy logic. The one I mentioned earlier, if you are working with image processing and signal processing, then go with the Gaussian. But for now, we will be focusing on these two. Okay, so let me just introduce to you the representation. Okay, look at this. Let's try to represent our values into the membership functions. So our first example earlier can be represented in this: short, average, and tall. Right? This is our crisp sets. This is our crisp inputs. So we said that any height that falls from 150 to 170, it is short. Okay? Any height from 170 to 180, we call them average. And then from 180 to 210, we call them tall. So these are our crisp inputs. And these crisp inputs now, we will convert them, or we will put them into our membership functions. If you will see this portion of the of this illustration uses trapezoid, right? It's using trapezoid. If you will notice, this one is a trapezoid. Half of the trapezoid, it was using this. Okay, so to represent short, we have 150 to 170, and then the average here, which is 170 to 180, is represented by a triangle, if you will see. And then the tall here is represented by 180 to 210, with the trapezoid. Correct? Now look at this. Let me emphasize one thing here, but I want you to notice it. Look at this. If you will notice in this example, there is overlapping here, right? Have you noticed this? This overlapping here. Correct? So between 165 and 170, there's an overlap, meaning the height that falls between 165 and 170 can either be average in height or short in height. Correct? Because they are in the middle, like the examples I gave to you earlier. So there are values between 165 and 170 could be considered either average or short. So we have to categorize this to be either short or average later on. And then same here, the values from 180 to 185 can either be categorized as average or tall. But the values from here up to here, there's no argument, they are tall. And the values from 150 to 160 here, there's no point of argument, because obviously they are short. So in this representation, we can now convert this value into either 0 or 1, or any value in between 0 and 1. So for us to calculate these values here, we have to go with this what we call a membership function. So the membership function will help us to determine if a certain height falls on a specific category. Let's say, for example, if I'm going to calculate for this point here, it would be equivalent to 0.4, or it could be also 0.1. So depending on the result of the calculation, which I will show to you later how to calculate it, we could convert these real life values into fuzzy values. Okay, so at the bottom here, we call this crisp values, and then the values here in the vertical in this column, we call them the fuzzy values. Okay, Look at this. So let's go with the first one, which is triangular membership function. So to convert a crisp input into a fuzzy value, you just have to observe this, okay? Anything outside the triangle, okay? Anything outside the triangle, automatically they are 0. Okay? 0, 0. Okay? Anything inside the triangle from this point up to this point, okay, the value can range from 0.1 up to 0.99. You have to note that. Okay? So in order for you to determine that, you could follow this rule. So you will see it says in here, if your value, let's say for example this is x, is less than or equal to a from this point, automatically it will get 0. Okay? Next, if your x, this one, is greater than c or equal to c, this is our c here, if it is equal or greater than c, and then it will get 0. Okay? Now, if my x, let's say for example, is in between a and b, if my x is between a and b, I have to follow this calculation. Okay? X minus a over b minus a. Okay? If my value falls here, okay, for my x, if my x is between c inclusively, okay, if it is here, and then the formula I'm going to use would be c minus x over c minus b. So this will be the formula. Okay? So if my representation is like this, please remember the representation of this. Any question? Any question here?
Repeat again, Doctor.
Okay. Let me just repeat. I think I have to copy this and put this in the whiteboard so that you could see it clearly, because I cannot write properly here. Let me just remove it here. Let me just copy this, okay? Copy and put it in the whiteboard. Okay, so let me just show to you this triangle here. So we call this triangular. So this is the calculation. We will determine the value of x, okay, in this example. So we want to determine the value of x. You have to remember, we want to convert x. Okay, let me just write the letter here better. So x here is our crisp input, okay? So when we say crisp input, this is a real life value, okay? Real life value. Okay, example of this one, example is, let's say for example 100 meters, okay, distance. Okay, so we want to convert this, we want to convert x into a fuzzy value. Okay, so for you to convert this one into fuzzy value, you have to follow this membership functions I've told you earlier. Okay, for you to convert this one into a fuzzy value. So you have to remember, take note of this, okay? Take note, passive value can only be from 0 to 1. Okay, the value can be from the range of 0 to 1. Okay, so basically you want to convert this real life value into 0 to 1. In order for us to convert 100 meters, let's say for example, into 0 to 1, then you have to calculate it, okay, using this formula. So to begin with, okay, let's go with the first one here. If my x, let's say for example, I have an x value, okay, if my x, this one, my x is greater than this, okay, is greater than or equal to my a, the value should be 0. Okay, you have to take note of that based on this rule. Okay, if my x is outside this triangle or equal to a, okay, from this point, okay, so the value of x will be automatically 0. Okay, you have to remember that. Same thing here. If my x is located here, the value of my x is located from here up to this portion, okay, automatically the value of my x will be 0. Okay, you have to remember that. So if my x is greater than or equal to c, and then it will get a 0 value as per the rule here. Okay, now if our values is within or inside the triangle, let's say for example x is within the triangle here, then you have to use any of this rule. Okay, so if my x is in between a and b, okay, is now between a and b, from this point up to this point, okay, is between my a and b, then I have to follow this formula. Okay, so this formula I have to follow. So I have to follow the formula x minus a divided by b minus a, close parenthesis, because this is we have to subtract first before we divide, so we have to follow this formula. Okay, so if it is here, Control Z, okay, okay, if it is here, I hope you can't see my illustration here. Okay, okay, if my x now, if my x is between this and up to c, okay, meaning my x is residing here, then I have to use the formula of this, which is, the formula is what is the formula? The formula is c minus x divided by c minus b. Okay, if my x is residing on this side. Okay, so these are the formula you're going to use. Clear? So what you have to see is you have to observe the value of x here, where it is falling into. Okay, if it is falling in this side, then you have to follow this formula. If it is falling in this side, then you have to use this formula. So everything that you need is here in the representation here. Okay, so if it is falling here outside the triangle, anything beyond this line would be 0. Anything beyond this line or within this line would be 0. Now let's proceed to the next function, which is the trapezoidal. Okay, for the trapezoidal, same. If you will see, same concept with the triangle, right? But in this time, we are using four vertices, A, B, C, and D. So compared to the triangle, we only have 1, 2, 3, 3 vertices, right? So we have a little bit, we have likely more formula to use here. Again, let me copy this in the whiteboard so that you could see it later. This is for trapezoidal. In this example, if my x, okay, if my x is here between the two, in this, okay, the value of x would be 0. Okay, so you have to note on this, the value of x is 0 if it is residing on this portion of the graph, I mean the diagram. Okay, so same thing, if my x resides on this side, if my x, see, it becomes 0 if it is located on outside here, so it will be automatically be 0. Okay, so you have to look at that. Okay, now if my x is between A and B, this one, it's between A and B, my x, let me just erase this point here, I don't need these points here. Okay, if it is here in between, okay, it's in between here, let's say for example, so I'm going to use the formula, which is x minus a over b minus a. X minus, close parenthesis, x minus a over b minus a. Okay, if it is here, so this is the formula. Okay, if b, I mean if x between b and c, automatically it will get 1. Okay, let me just put a note here, I forgot. So if it is here, the formula is like that. Okay, so if x is located in between b and c, so x becomes automatically equal to 1. Okay, so please remember this. Okay, if my x is here. Any question here? So if my x is residing in between C and D inclusive, okay, so I'm going to use the formula d minus x over d over c. d minus x over d minus c. So we have to place it, Control Z, we have to place it somewhere here. Let me just resize it. Okay. You have to develop, okay, this is the problem. You have to develop a fuzzy logic system for intelligent speed control system for a car. So the inputs of your system is the ambient temperature, which is taken from the car sensors, and cloud cover data taken from the weather data server. So your system should suggest the driver what is the appropriate speed based on the inputs. So let me just draw to you the diagram so that you could have a grasp of the problem given. Okay, so this is the problem. Let me just illustrate it to you. So our problem is having these inputs. Okay, so this is our fuzzy system. Okay, so we have our fuzzy system here. It has two inputs. Okay, so input 1 is about temperature. Okay, so this is the first input. It's about the temperature. The second input is about the weather, right? The weather, the cloud, or maybe this. How do we call this in in Arabic? This if it's cloudy or not. So just let's call it cloud, okay? Cloud, or the density of the cloud. So this is your second input, okay? So your output, they want you to calculate the speed. So or what should be the speed of the driver? Okay, so this in the middle, we call it the fuzzy system. Okay, this is a fuzzy system in the middle. Okay, look at this. So with this input, temperature and cloud density as inputs, again in our fuzzy system, we're going to calculate what should be the speed of the car. Okay, what would be the speed of the car based on this given inputs? So we have to calculate it using fuzzy system. Okay, given this inputs here and input here, this input here and input here, what would be the speed of the car? So we have to calculate it. So let's proceed with the given facts here. Step 1. Okay, step 1, we're going to define the linguistic variables and terms. So under temperature, we have these variables, as I've told you earlier. We have temperature for temperature we have freezing, cool, warm, and hot. So we have how many groups here? How many groups for temperature? We have 4 groups, right? One is freezing, second one is cool, the third one is warm, and the last group is hot. Then for the cover we have sunny, okay, partly cloudy, and overcast. So meaning sunny, no clouds, partly cloudy with some few or with some clouds or few clouds. Then overcast means the sky is full of cloud and there might be the tendency to rain. We know it, right? If it is sunny, less tendency in raining. If it is partly cloudy, meaning there's a chance to rain or not. Then if it's overcast, there's a big chance of raining. We know it, right? For the clouds. So the speed is categorized into 2 only, which is slow or fast. But in real life, you can't put something in the middle, which is medium. But basically, in this example, we're going to categorize speed into 2 only, which is slow and fast. Okay. So with this inputs at hand, okay, what will be our output? Let me just put a highlight here so that you will know what I'm pointing out. So these 2 here, we call them the input, and this one here, we call it the output. Okay. So what will be the speed of the car? Let's say, for example, if the temperature is freezing and it is let's say, for example, freezing and it is overcast, what do you think is the speed? If it is hot, the temperature is hot, and then it is sunny, what would be the speed of the car? Should it be slow or fast? So again, depending on your rules in your inference engine, depending on your rules, we could determine the level of speed, if it is slow or it could be fast. Next, after defining your linguistic variables, let's now draw or construct the membership function. Okay. So normally on problems in your examination, mostly in the test and in the final exam, actually, I will be giving you a table. Discussing to you the ranges of the values. Okay, you might be seeing tables like freezing 10 to 50, cool 30 to 70, warm 50 to 90, hot 70 to 110. So from that table, you're going to draw your membership functions. Okay. By the way, next meeting I'll give you another example for that. You will see how we will construct the membership functions based on the table that I'm going to give to you. But for this example, okay, the temperature, freezing, cool, and warm. This is the categories of the temperature. If the temperature is from 0 up to 50, you look at this one. Okay, this point started here. Okay, started here. So this is actually 0 here. Up to 50, this is for freezing. Okay, this is for freezing. Cool is 30 to 70. This is for cool. 30 to 70. Then warm is 50 to 90. 50 to 90 is for warm. For hot, we have 70 up to 110. 70 to 110. Okay? So, if you will see, there is a fuzziness. Okay, there's some values that share 2 categories, correct? Look at this. The values between 30 and 50, they share between freezing and cool. Likewise, for 50 and 70, they are sharing with warm. Then from hot, we have 70 and 90 here. So same with the cover for sunny. For the sunny, you will see from 0 to 40, from 0 here up to 40, we have sunny here. Okay, and then from 20 to 80 we have partly or partly cloudy, and then from 60 to 100 we have overcast. So this is how we represent our membership functions. So you will see one here is using trapezoid, and the two here are using triangles. Okay, this also is using trapezoid. Same here, we are using trapezoid here, and we are using trapezoid here also, and we are using triangle here. So I guess you will be able to convert the values now into fuzzy values, right? The crisp inputs into the fuzzy values. So for the speed, we draw the diagram. Slow starts from 0 up to 75. Okay, this is for slow. For fast, the value starts from 25 up to hundreds maybe. Okay, so there is a gap, not gap, it is overlap. There's overlap between slow and fast, which is from the values 25 to 75. Okay, and the unit of speed used in this example is miles per hour. Okay, it's miles per hour, I guess. It's not meter per hour. Okay, it's miles per hour, because normally cars, we don't use meter per hour here. We are using kilometers per hour. But in this example, we are using miles per hour. So you have to construct the rules. Okay, so we are now on the third step, which is constructing the rule. And in this, it says, if it is sunny and cool, if it is sunny and the temperature of the car is cool, then you can drive fast. So this is the rule here. So to represent it in discrete mathematics, this is the representation in discrete mathematics. Cover, close parenthesis, sunny, and temperature is cool, and then the speed should be fast. Okay, next, if it's sunny and hot, okay, if it's sunny and hot, then you have to drive fast. So this is the rule. So to represent it in discrete mathematics, cover, close parenthesis, sunny, and, okay, and, so when you see this symbol means and, okay, this symbol means or. Okay, next, if it's cloudy and warm, if it's cloudy and the temperature of your car is warm, or the temperature of the environment is warm, then you have to drive slow. If it's cloudy and cool, if it's cloudy at the same time the temperature is cool, then you have to drive slow, meaning it's dangerous. Okay, so these are the rules that we have. So if cover is sunny and temperature is cool, we have to drive fast. If the cover is sunny and the temperature is hot, we have to drive fast. If the cover is cloudy and the temperature is warm, then we have to drive slow. If the temperature, if it's cloudy and cool, then you have to drive slow. So basically these are the rules. Do you have any questions here? So you have to remember, we're going to arrive with our decision later based on these rules. Okay, we're going to infer, we're going to make a conclusion or a decision. So inference will be based on your rule base here. So this is your rule base. Okay, so all the rules are here. And thank you so much for your time for attending this today's class. Thank you so much, and masalam.